Okay, we continue with vector calculus, and what we've done so far is we've talked about derivatives of scalar functions. So a scalar function is something that takes in some number of variables. Could be 1, could be 50, and then it spits out just one number. So for us, a real number in quantum mechanics, maybe a complex number. But D is the dimensionality of the input space. You know, you'll usually think about that as x, y, and z. So 3D in, and then just one number goes out. So for an example, temperature is a scalar function. You give me a point in this room, the x, y, and z coordinate, and then I tell you what temperature it is. One number comes out. Okay. And then we talked about the gradient of that, which you usually think about or used to thinking about as a thing that you do to your scalar function, and you kind of take these partial derivatives and give them a unit vector. But what we'll do is we'll talk about it as a vector itself, so this vector del. And when it operates on a scalar function, what I'm left with is a mapping from d dimensions to d dimensions. So vector in, vector out in some sense. And del itself, the gradient operator, is a vector. It transforms like a vector. So you'll see it written in this, kind of very abstract way, where in a d-dimensional space, it's got d unit vectors and d partial derivatives. And that kind of makes your eyes bleed at first. But if you ever get confused, just think about 3D Cartesian. And in 3D Cartesian coordinates, the gradient operator is I hat partial x, j hat partial y, k hat partial z. So that's scalar derivatives, and we talked a bit about their geometric meaning. So now what we want to talk about is derivatives of vector functions. And we're going to restrict ourselves to two really important cases. So we're going to talk about vector fields and vector functions. So a vector function is one number goes in, a vector goes out. So you can actually almost think about it as the opposite of this. And I'll use a different letter F so we don't get confused. So maybe we'll use R is a great letter for this for a reason you'll see in a second. So a vector function of one variable would be a mapping from R to whatever the dimensionality of the space is. So why choose R? Because a really good example of this is the position vector in mechanics. So an example would be position and velocity. So you tell me the time, and then I tell you it's x, y, and z coordinates. So one number goes in, three numbers comes out. And then another good example would be velocity, and another good example would be acceleration. Say vx, vy, vz. Okay, and this will be really quick, just a reminder. What the geometric meaning of this is, well, let's say that I wanted to take dr dt. I only have one input variable, so that's the only thing that I can change and ask about rates of change. So dr dt geometrically is the limit as delta t goes to 0 of r of t plus delta t minus r of t, and you guys know what it means to be the difference of two vectors, but I'm going to draw it on a picture. So this is a point. So that's r at point t. And then at some time later, you're over here. And somewhat grandiosely, I'm going to, maybe this delta t is a pretty big delta t. At delta t later, I'm over here, and you can think about even sweeping out a trajectory. So I'm sweeping out a trajectory as I go along there, and that's the curve that r of t sweeps out. So that's r of t itself for some arbitrary t. And what this is I subtract these two vectors, and then that would be the vector that goes from here to here, and I take the limit as delta t goes to 0. So that's the geometric meaning, but at some point you dispense with that, and you just say, look, I know how to do this. When I subtract two vectors component-wise, I subtract x from x, y from y, z from z. So ultimately what I get is just plain old ordinary component-wise derivatives. And vector calculus of vector functions of one variable is the easiest thing you've ever done. It's just 3 copies of plain old ordinary scalar 1D calculus. Okay, so that leaves us with everything else. So vector functions could be arbitrarily something G, which is a mapping from our A copies of the real line to D, the dimensionality of the space. So what we just did is the really easy case of A equals 1, right? So just one real number n, and then a vector comes out. So it turns out in between 1 and D is you have to treat on a case-by-case basis. What we'll talk about, because they're really important, are what are called vector fields. So and a vector field, G, is vector in, vector out. So what's an example of a vector field? I'm sure you said something really thoughtful. I just can't hear you because this is a recording. A really good example of a vector field would be like the electric field. So the electric field E. The way the electric field E works is you tell me a point in space, right? So this thing is located at X, Y, and Z. And then I tell you that there's a vector located there, and it's got these 3 components, right? So basically, imagine that the universe is bristling with electric fields or magnetic fields. Every point in space contains something that points like this. So vector fields you might visualize in that way. And in class, we'll crack out some Mathematica to do some better visualizing than I'm able to with my crappy drawings. But I've got a box of space, and basically it's full of arrows, and there's an arrow at every single point in space. And the arrows change as I go from one spot to another, and therefore I can ask calculus-like questions, rate of change questions. Okay? And it turns out this is a more complex problem. This is why you probably spent an entire quarter on this. So we'll just really go through a review, quick review, and we'll do it by talking about del as a thing in and of itself. So the 2 most important things that you can ask about vector fields are the divergence and the curl. And first we'll just define them. So this is a very mathematician thing to do, is just like say this thing exists, and then maybe someday later it turns out to be useful. And we'll do it in Cartesian coordinates as a gentle introduction. And then later we'll talk about what the geometric meaning is when I can, bring up better visualizations with Mathematica. So the nice thing about del is you know exactly what this is without me even really needing to define it. It is the scalar or dot product of the del vector or operator with whatever vector field you have. And this is a vector, that is a vector, so you already know how to do this. So we really just need to maybe have an example. And you can think about this as a force. Forces are vectors. and you can also shame me for not having unitful things on this. So pretend that there are constants on this that bear units. Okay, and then the delightful fluidity of notation. I'll use the angly brackety things, and we've got x with x. Boy, that's a lot of nothing. Partial x, there's no x in there, so there's nothing to do. And then partial y, there's nothing in there, nothing to do. And then partial z, there, whoops, sorry, shouldn't have these. As it happens when you get too fluid with your notation. So that implicitly is the x and y and z components. And then partial z, that there is something to do. So we get 2zx. So this is 2zx. And just as the dot product of two vectors is a scalar, the dot product of the gradient operator with a vector function is a scalar function. Right. So generically what we can say is this is a mapping from R3 to R. So vector goes in, you got to tell me x, y, and z, and then just a number comes out. Right? And the reason to keep kind of bringing this up, this notation, is for one thing, higher levels of physics, people use this conversantly. And secondly is that this will be the way of understanding higher order derivatives. Okay, so as promised, I guess we could, through this example, write down a general Cartesian formula for del. So partial fx with respect to x plus the partial derivative of the y-coordinate of our vector function with respect to y plus the partial derivative of the z component of our vector function with respect to z. So dot product means match x with x, y with y, z with z. So this would be del dot f. And that would be the general Cartesian formula. Okay, and likewise with the same example, we could go through curl. And again, we haven't really talked about what these mean yet. I don't know how much of that you guys have seen. About circulation and divergence as spreading out of vector fields. So I have del dot f, or del cross f. And this thing should take two vectors and return a vector because it's a cross product or vector product. And then we got x component, y component, z component. And this looks more fun and promising. Okay, so I will crunch through this. We got the I hat. There's no y there. There's something there. So that's one I hat. And then we got the weird minus sign, so that's something. So that's z squared, and then z with that, that's nothing. J hat. And then plus, because that's an odd permutation, so that's nothing, and then that's something. So that's minus minus is plus 2y k hat. And then cleaning that up, I will just write it like 1 minus z squared 2y. So as promised, this is a mapping from vectors to vectors. Okay. One of the things we're going to not talk about in this class is which dimensions you can actually define these things in, del grad, or gradient and divergence and curl. Could you do it in 5D or 7D or something like that? Turns out to be like kind of an interesting question. But what we have by looking at this is the general Cartesian formula. Cartesian or rectangular coordinates. And honestly, this is heavy in notation, so this is the determinant of this matrix. And the formula would involve, real formula would involve writing out all of those grubby permutations, but we're not going to do that. Because I presume you guys know what this means. Okay? Okay. So what do these things actually mean? Again, we'll get into it a bit with some Mathematica demos, but essentially what this is a measure of, roughly speaking, and it's not like perfectly true, but what I want you guys to realize is that if I have a box of vectors, so I've got a box and it's like bristling with vectors, there's more than one way that they can change. So they can change, for instance, by just getting longer. So all of these, they all point in the same direction, but as I move along some direction, they just get longer. So this is a type of changing vector field, for sure, right? They're definitely changing. And this is the thing that gets kind of captured in both of these potentially. That's kind of what you would think maybe with a scalar function. The scalar function just gets bigger or smaller. That's the magnitude. But what these things do that's unique and doesn't have an analog for just scalar functions is there are other ways where vectors that don't change in length, so they don't change in magnitude necessarily, but they change in the way that they bunch up or spread out. So what divergence does in some sense is it measures the spread of vectors. So here are a bunch of vectors, and they're spreading out. But their magnitudes aren't changing, right? So this is a different type of change. And then maybe they come back together. So they, these guys come back together, and those guys come together. So these things spread and contract. So this is, in a sense, what divergence measures. This would be a region of positive divergence, they're spreading out, and this would be a region of negative divergence where they're coming together. And there's another way for these to change, is that we could swirl. Again, to the best of my artistic ability, I'm trying to draw vectors that all have the same magnitude. So their magnitudes aren't changing, but what is changing is that they're spinning around some point. So this is, in essence, what the curl measures. So curl measures, in some degree, circulation. Sometimes you'll even, I think, hear it in really archaic textbooks as circulation. And what divergence measures is the spreading of the vectors. Okay, so we got one last thing to do, and that's the payoff for our cutesy poo mapping Rn to R whatever notation, is that we have a way of simplifying our lives if we're presented with an attempted higher order derivative based on the gradient operator. And this is the game that we'll play, at least for now. About what's permissible. So I'm going to write out a whole bunch of stuff. So let's say that we have vector fields. A and B. So that means, for instance, A is a mapping from R3 to R3. Or another way of saying it is, at least in Cartesian coordinates, I've got to tell you x, y, and z, and then a 3D vector comes out. And a scalar function, f of x, y, and z. Which means that f is a mapping from R3 to R. Okay, so these are the things I'm going to play with, and I'm just going to write down some stuff. And if you've been paying attention to this, this whole dimensionality stuff, there's going to be a whole bunch of things that are permissible and are not. So don't worry about the fact that I'm looking at a paper. Just pretend I'm making stuff up. And shame on me for this last one. Okay. So the first thing we can do is just say, like, is this even a possible thing that we could write down? So in single variable calculus, you can write down however many derivatives you want. Maybe you get to 0, maybe you get to something that doesn't exist or has undefined points, but you can just keep writing down derivatives. Not so much with del. So I think that this is a thing that doesn't exist. Like, it's ill-defined because I can't take the curl of a scalar function, right? So this is something that spits out just one real number, not a vector, so this is not defined. So what else is not defined? Well, I can see a couple of other things. I'll leave these. We'll go over these in class, actually, is probably the best way of doing it. So what about that, for instance? Is that OK? What about that? Is that OK? OK, so here's the other interesting thing, and we'll get into a couple of these, is that some of these things are defined, but they just don't exist. So for instance, the curl of a gradient is identically 0. And the divergence of a curl is identically 0. So some of these things you can just, by virtue of counting variables, you just like, it's a poorly defined statement. There are things that do exist, and they do have special formulas for them. So I will write down one of these special formulas, and you guys might actually have to prove this. This is a special formula that shows up a fair amount in electricity and magnetism. And the way that you would prove it is probably by using Cartesian coordinates and actually writing the whole thing out, I'm sorry to say. So we can have things that vanish identically. So for instance, curl of gradient identically vanishes. This is true for all f. Like any scalar function that you talk about can dream up, this is true. And the divergence of a curl is also 0, scalar 0, because that's a divergence for all vector functions A. So these are vector identities. And the other thing that happens is we can also have useful question mark formulas. In an E&M class, you might be told that this is a useful formula, and then maybe you'll just like suspect that that might not be the case when you actually start trying to use it. And I'll even leave off the vector hats because I think you know what they mean at this point. OK, you can either take two curls, or you can take the gradient of a divergence and the divergence of gradient. So actually, I think this is pretty useful because I would rather do that than that. So that's kind of the story with higher order derivatives. Usually what happens 9 times out of 10 is you're reminded that the thing has a useful formula. These are really important to remember. So the fact that those the curl of a gradient and the divergence of a curl vanish are really important to remember.